Okay, so let's begin. I'll talk about let's talk about two basically sort of applications today. We already talked about certain examples and applications, but let's say focus on two such more applications today. One of which will be from the first part, which was our study of open quantum systems. So this will be on how to understand, let's say, chaos from open system dynamics. Let's focus on this first. And the references will be a couple of our papers which we wrote recently. Tingle and not sure. So chaos, as we understand, is basically the phenomenon where we, let's say, if we start from two points in the phase space which are very close, let's say, defined by some epsilon, if we let them evolve, they become exponentially separate from each other. And the usual measures of quantum chaos that we know of is the first one is, of course, the Lyapunov coefficient. Which is basically if we do something like this, take the expectation value of this commutator square. So this will, if we expand this commutator square, this will look like some 4-point functions, combination of 4-point functions. And from this actually we can get some, let's say, this kind of 4-point functions, which is basically out of time order. And this, if we look at the growth of these out of time ordered correlators, which people also call ODOC, this shows this e power lambda t kind of behavior for typically chaotic systems. Especially this lambda is called the Lyapunov coefficient, and this saturates a bound for chaotic system. So this lambda is then some 2 pi over beta, where beta is the inverse temperature. So this bound is saturated. So this equality holds for chaotic systems and chaotic evolution. So there are other signatures of chaos that one can look for, which are more studied in the literature of quantum physics and in overall in literature. So some of those are basically level statistics. So let's say if you are given a Hamiltonian, how you can say whether for that Hamiltonian the evolution will be integrable or chaotic. So the way to do so is, if you are given a Hamiltonian, firstly reduce the symmetries, or sometimes people call resolve the symmetries as well. Resolve the symmetries of the Hamiltonian. This is to make sure that, let's say, if you are looking at the spectrum of this Hamiltonian, we will get certain number of eigenvalues. And the way level statistics is done is to look at different eigenvalues. Now, if we have some degeneracy due to the symmetries, we can have one eigenvalue more than one time. But if we plot something like level statistics for those degenerate eigenvalues, it will always end up giving us some distribution which is for integrable cases, which is the Poissonian distribution. But we don't want that. We want to be able to distinguish the integrable and chaotic system. So the way to do so is primarily to get rid of the symmetries, let's say your Hamiltonian has certain symmetries that it can have parity symmetry, it can have other symmetries. You want to reduce the symmetries. For example, in Python there is a very simple operator through which you can get rid of the symmetries, which is called Q-spin, which you can implement on spin chains and so on. So secondly, what one has to do is after reducing the symmetries, so I'll have, let's say, non-degenerate eigenvalues, non-degenerate spectrum, and list these in ascending order. So what further one needs to do is basically then look at the symmetry eigenvalues and difference of them. You will also have to, in some cases, you have to divide it by something and define some new parameter. And in fact, let's say from this I can define a parameter S, and basically plot ES versus S. So what it says is that basically what this plot is going to say, don't focus on this S phenomena or anything. What this plot basically has to say is how closely spaced or not closely spaced the eigenvalues of the Hamiltonian are. And the typical nature of integrable and chaotic theories are that for integrable case you get a Poissonian distribution, and for chaotic theories you get something called so this is for integrable, which is Poissonian, and this is for chaotic, which is called Wigner-Dyson. So after, but this point was that if you don't resolve the symmetries or do not get rid of the degeneracy, then this plot will always end up looking like the Poissonian distribution. But only if we resolve the symmetries, then we can, for a chaotic system, we can get something like this, which is the Wigner-Dyson. And okay, so this is, for example, one way to look at, another way to look at or distinguish integrable and chaotic theories. Then there is something called the spectral form factor. This I mentioned. So you have to put in the condition when you are writing the Hamiltonian. The Hamiltonian, let's say, will be some n cross n matrix. It could be. Then, if you resolve the symmetries, so from this n cross n matrix, you should get n eigenvalues in general. But resolving the symmetries means that you have to put in the condition that if you, let's say, use all spin up, in some cases it could be this kind of symmetry, that all spin up and all spin down, those states will give you same kind of results. So, yeah, basically the simplest way, it is hard to do numerically, but the easiest way to get rid of the symmetries is, I mean, this is basically the way how you put in the condition that you want to reduce the size of the Hamiltonian as well, depending on the eigenstates of the Hamiltonian, which give you the same eigenvalues. And that you can, for example, do in different numerical codes in different ways. The easiest way to do it is in Python. You just implement a package called Q-spin, it will do it for you, let's say for spin chains. But for more general systems, it is not very trivial. Okay, so then the third thing is spectral form factor, which is basically from this Hamiltonian, you can compute the partition function of this Hamiltonian, and SSF is basically something like this. Which in fact you can this is for example just a phase. They will have to take sum over this. Of course, once you get this picture, you can compute such things. And for finite temperature system, if you have, let's say, some system that we talk about a little later, we will deal with, for example, infinite temperature system where your beta could be zero. If you take beta to be zero, then in principle, this will also go to some. This will in principle go to some one. So you don't want to do that. Even if you are dealing with infinite temperature where beta is zero, to numerically plot this kind of spectral form factors, what one has to do is to take some very small value of beta. So the difference between integrable and theoretic theories in this case is basically that if you plot SSF versus T, it always starts from some 1, then it comes down, and for integrable theory it keeps showing this kind of fluctuations. Fluctuations is similar to oscillations. Fluctuations and large fluctuations. And so this is for integrable. Very large fluctuations, and for theory you see again comes down, but this large slope primary growth and then arbitrary fluctuations is not actually shown. What it shows is that it shows the ramp, systematic ramp, and then it again fluctuates, but far this the amount of fluctuations will be far more less than the integrable case, and it will actually remain there. So this is known as the deep ramp and plateau behavior. So again, by looking at this spectral form factor, also one can distinguish between integrable and chaotic theories. So these are all different signatures, but these are tested beforehand, and we will talk about some other signature where for the, let's say, the closed system case, all of these have been checked, and there is a different integrable and chaotic limits that already exist for the model that we will study. But the property or the quantity that we will study will be not these things, but something called Kill-off complexity, where basically we will try to distinguish an integrable theory and a chaotic theory by looking at the growth of an operator, which is in some sense similar to the OTOC or the out of time ordered correlators, but here we will get a better understanding of precisely how the operator grows. So this is 4 is operator growth. So what we do here, let's say let me first write down the Hamiltonian itself that we are going to study. It will be the Hamiltonian of transverse field Dyson model. The couplings, the whole Hamiltonian is just permission. All of these couplings are real. This is the transverse field coupling. This sigma Jz is the transverse field limits that basically means the Hamiltonian. And basically, what is already known from the studies of the previous things that I mentioned, let's say the level statistics, spectral form factor, and so on, is that for h equals to 0, its model is always integrable. And for h equals to non-zero, it starts becoming chaotic. Of course, when I say starts becoming chaotic, basically what I mean is that how exact your Wigner-Dyson distribution is, through which you can say how chaotic it is. So it will start shifting from, as you increase h from 0 to some non-zero value, it will the Poissonian distribution here starts shifting to something like a Wigner distribution, and when it becomes more and more, whether the distribution is clearly Wigner or not, that's what I mean. It starts becoming chaotic at some point, it becomes maximally chaotic. So the parameter values for which people usually check the integrable and chaotic limits is for g equals to 1, h equals to 0. This is the integrable case, and h equals g equals to minus 1.05, h equals to 0.5. This is the, say, two ways to say theory is chaotic. More precise way is probably to write that is maximally away from integrable. So what we will do is firstly we will study the results that I am going to talk about are for n equals to 6. This is precisely because of our numerical limits. If you increase the system size more and more in a supercomputer, these effects will magnify more and more, and we will be probably able to make more clearer conclusions, but nevertheless for this also we get good enough conclusive results. So what we do is we start from a simple operator at time 0, which will be identity at all the sites except for the third site. This is just to ensure that my operator was somewhere in the middle of the lattice that I am considering, and I want to see how this operator splits to the whole system as I evolve this operator with this Hamiltonian, which has support over all the sites of over which this Hamiltonian is defined. So basically, in Heisenberg picture, what we can write is IHT goes into IHT. We expand this, what we get, expand both these exponentials, what we get is this. These dotted terms are again I square, I cube, d cube over 3 factorial, 3 such nested commutators over O0. And basically this nested commutator action on some operator, this is basically a super operator acting on this operator. This can be treated again as Liouvillean. Okay? And this Liouvillean, this notation you can already see this similarity with this or this notation with the, for example, the quantum map that we studied while we were studying the GKSL equation and so on. So this is eventually going to be for open system. This is not just this, but plus something, plus some non-Hermitian part is going to give us our map that we discussed there as well. But for now, just let's call this union super operator. And basically this expansion that we wrote down here, we can simply write this as this acting on. So if you take a look at this, look at this expression, what is happening is we started from O0. Let's say if we try to think of as this as small time orders probability, then after some time this is not really small time orders, but you can think it of as time steps or as how many Liouvilleans or Liouvilleans are acting on this O0 and making this O0 spread to other parts of the system. For example, if you compute this, you will already see that this one side operator will become 3 side. Then if you compute 2 times, you will see it can become some other 3 sides. There is no support, not trivial support on third side, but not trivial support on other sides and so on. So it will keep becoming keep having support on more and more sites, and at some point it will reach the size of the total system that is all the 6 sites will have non-trivial supports. But the consistent way to study this increase of support and how this operator is growing and spreading is done by uh, orthogonalization procedure, which is known as Lang's orthogonalization. So, so all of these that I am talking about till now are for closed or isolated systems. I will mention when I go to open system. So what we will do is we will treat this O0 as some zeroth element of a basis, and we will denote this as some O0 state like this, where this will then become a operator kind of thing. And if you want to basically, so these things that will follow from repeated actions of this Liouvillean, they will not actually be orthogonal in any definition of inner product. So what we want to do is we want to act on this O0 with this Liouvillean, and we want to construct a next basis element O1 which is orthogonal to O0, and all of such basis elements that we will construct will form an orthonormal basis. Gram-Schmidt, but we will basically look for, since this H, this operator is such, super operator is such that this doesn't give you, in the right hand side, you will, let's say, N acting on O0, you will not get anything proportional to O0. You will get only something proportional to O1 and something proportional to either as the previous thing, because this is a commutator. But in the most general case, you can also get something proportional to O0 and so on. So we will try to form a tridiagonal basis. That is our goal. So this is what Lang's orthogonalization procedure does. So primarily to form such orthogonal basis, we need to resort to some definition of inner product. So the definition we opt for is this Frobenius inner product or infinite temperature inner product, which is basically just this case of identity. And the Lang's procedure basically can be written as this simple step that L acting on any ON will give me some coefficients which are called Lang's coefficients. So let's say if I am already acting on ON, I sort of already know the Bn and ON minus 1. What I do is that I will act on ON, I will subtract this part, and then basically whatever state that we get, that we will normalize. From that normalization, we will get this Bn plus 1. The state that we generally get will be some An, let's say, which will be not normalized to begin with. We will have to normalize that to get these new set of coefficients. Now we will know Bn plus 1, and we can similarly act on On plus 1 to construct On plus 2. So let's say our final state, so that the basis that we form this way, let's say some O0 to OA, let's say, is known as the Krylov basis. And in this Krylov basis, the typical for finite dimensional system, for example, here our Hilbert space dimension will be how much? So there are 6 sites. So our Hilbert space dimensions will be basically these matrices are 2 cross 2. So our Hilbert space dimension is 2 to the power 6. Okay. For a finite dimensional Hilbert space. Let's say for D, the Krylov space dimension is shown in this paper. In 2020, there is a paper called Age of Krylov Space, mistaking the title, but Age of something. There's a paper on this where they showed that the Krylov space dimension is has an upper bound, which is this thing, d square minus d plus 1. And so let's say we have this Krylov space dimension, and then in that basis we can write the final state just for convention. We write it as a this 0 to t minus 1 t such basis elements, and we have an expansion of this kind. Well, here are the time dependent coefficients. Now what we do is if you take this and remember that this operator thing that I wrote, this OT used to follow a Heisenberg equation of motion, which is basically ddt of OT is IH comma OT commutator, which you can write it as this. This was my Heisenberg equation of motion. Now, if I use this expansion of OT in this equation, what we get is a differential equation on phi and t's. And this equation is basically, this equation looks very similar to discretized Schrodinger equation, something that one gets from study of time binding models as well as Banks model physics. So I'll assume that while constructing the basis, we already have known these Lang's coefficients Bns, so we know all of these things. We have to solve these equations recursively to know all the phi ends.
This comes from type-bending Hamilton method, and if you type-bending from type-bending Hamilton.
Yeah. I mean, this looks similar to, from this you can think of these phi ends. Basically, you can motivate yourself that since this looks like exactly like a time-bending Hamiltonian Schrodinger equation, discretized Schrodinger equation, you can think of this phi ends as probability of the operator O at time t, the operator O at time t being innate Krylov basis element. This phi ends denote that probability, and of course for a closed system you would expect that then it should get the sum of probabilities to be 1, which is basically equivalent to saying this thing 0 to t minus 1. This is by closed system again. This is a version of saying that my system is going through unitary evolution. This indeed happens. For example, another fact that you should remember is that while solving these equations recursively, we have to impose boundary conditions of this kind that phi 0, we know that at time 0 our whole operator was situated at the 0th Krylov basis element that we started. Phi 0 will be all that should be contributing here. Every other phi ends should not contribute at time 0, and therefore any other phi n at time 0 in general, even for any general phi n, we can in fact write use this boundary condition. And so this was from the probability kind of thing. The probability has to be, complete probability has to be 1. This is a recursive way to construct a basis. So you can use different ways to construct an orthonormal basis. Gram-Schmidt is the most general way. This is a specific version of Gram-Schmidt, known as Lang's orthogonalization, where one takes such tridiagonal matrix elements, and from this what you will essentially get is basically a form of this nucleus that was acting on the operator in terms of these basis elements. And this basis will be basically tridiagonal basis with diagonal elements becoming all 0, and the bn's will come like this. So here we will get something like b k minus 1 and k minus 1. This kind of tridiagonal basis you can form this way. And basically the definition of field of complexity is the average position. So we already discussed that phi n's are my probabilities of the operator O in the image field of basis at time t. So average position of the operator at time t, which is basically again a sum over n going from 0 to t minus 1. N is the position, so we have to take the n expectation value in terms of my phi n t square. So this is exactly same as what we do in case of usual quantum mechanics. And this is defined as the field of complexity, which will be just a function of t. And yeah, so now let's discuss what happens, what one sees if we do this for this transverse field Hamiltonian, IC model Hamiltonian that we wrote. And remember that integrable case was h equals to 0, g equals to 1, h was the transverse field coupling, and chaotic case was h equals to 0.5, g equals to some minus 1.05. So actually what happens is this, when do you stop implementing this algorithm? There should be some stopping mechanism as well. Otherwise, we'll always end up doing this step for infinitely many times. So the way to do so is whenever you stop having linearly independent basis elements. And how do you see that your basis elements are not linearly independent anymore? That at some point you will find that this bn plus 1 will come out to 0. There are no further elements. So what we expect is that at some point this this will probably not be 0, but this will be very close to 0. The next step we had done, we would have gotten a 0 here. So there is the way to stop. And so the behavior of bn's, if you plot bn versus n, this actually, from this plot one can distinguish somewhat the integrable and chaotic cases. And how does it behave? So the chaotic cases are go primarily. This growth happens, this n you can think of as an analog of time at this point of time, but yeah, so how many number of iterations that we have taken that it says, and until the number of iterations till which this operator has reached the full system size, this bn show growth. So this is sort of, you can, the primary growing region, you can associate this time scale to the scrambling time scale, until which the operator was still scrambling. Then what happens is it remains sort of effectively saturated for some amount of time. Of course, it remember that it has to come to 0 for us to be able to stop the algorithm. And this effective saturation time till when it remains effectively saturated, this basically has to do with something called Heisenberg time scales. So Heisenberg time scales, and after scrambling time scales and between Heisenberg and scrambling time scale, actually the theory shows sort of the quantum correlators become very much different from the classical correlators, and there you can, but they remain small enough that, for example, here you can see this effective saturation due to the fact that the quantum correlations are non-zero, have a non-zero effect than the classical correlation, but it is not too big. Afterwards, it starts coming down to 0. Now, when we stop, let's say at this t minus 1 number of iterations, we stop our algorithm. But this coming down to 0 procedure has a very large fluctuating behavior of bn's, This fluctuation will be much more for integrable case, and these fluctuations will be much less compared to the integrable case in case of the chaotic dynamics. And this particular these kind of fluctuations for the integrable case are known as field of localization. They say that the integrable case explores the field of space far less efficiently than say the chaotic case. And this initial growth was conjectured in a paper by Parker et al. 2018, where they said that the chaotic cases, so for chaos, the BNs before scrambling, let's say, in this case, or in the most general case, if you have an infinite dimensional system, BNs asymptotic behavior of BNs are basically alpha n. These alphas have, I will not go into it, but these alphas have some relation to the Lyapunov coefficients as well. This alpha n behavior is specific to chaos, but since then, in some cases, people have also shown that in some cases of saddle dominated scramblings where it is not strictly chaotic, but it still shows BN going to alpha n. But the thing is that chaotic models will always differently show this. In some integrable models where you have saddles and so on, the integrable models can also end up showing this kind of behavior, but the chaotic models will always show this behavior. And so this is one way to distinguish integrable and chaotic situation. What happens for the corresponding complexities? There is also a way to distinguish the complexities, which is a basically time dynamics behavior, directly time. And here what happens is, if you have a linear growth until let's say P is scrambling, it will grow exponentially. The complexity will grow exponentially with basically this kind of behavior. You have 2 alpha t, where this alpha comes from this root. Then it will show a linear growth for this effectively saturated region between the scrambling and until the Heisenberg time is achieved. So this is much more larger time. So to be more specific, this is in terms of system size, the scrambling time scale goes as some log of system size. The Heisenberg time scale goes as e to the power s. So log of 6 for our n equals to 6, and Heisenberg time will be e to the power 6. And this time or this end of the basis, one should probably relate to something called the Poincaré recurrence time. Till Heisenberg time, the complexity shows this linear behavior, and then it saturates and remains saturated until the Poincaré recurrence time, which is known as double exponential of s. So this is recurrence time. So you can already see this is very hard to go till this recurrence time, because even for 6 size system it will be exponential of 6, which is a very long. And so it will remain saturated till then. And what happens in a integrable situation? It shows a primarily for a sublinear growth of these BNs until scrambling time. It shows a power law behavior which is less than the exponential growth. Then it again shows the linear growth. And at Heisenberg time, it shows a saturation, but this saturation value will be far less than the saturation value for the chaotic case. All of these parts sort of help you to distinguish integrable and chaotic dynamics, as well as different time dynamics. What is happening before scrambling, what is happening between scrambling and Heisenberg time scale, and what is the difference between them after the Heisenberg time scale. One can distinguish all of these things for closed systems. Now coming to an open system case, what happens in open system? So we'll have to introduce some Lindblad operators, L alphas and so on. And this will change. Yeah. These fluctuations are like very large fluctuations, but you will still be able to see that this fluctuating part will have a large width, that is what I mean, but it will still keep coming down to zero. Both will come down. Yeah.
What is the relation with these? This n was lifetime, but on the one hand we are saying scrambling time on the n-axis, and on the other hand we are saying scrambling time on the t-axis. So how are the ts and n's related?
So the way t and n's are related is likely saying that as many times as you act on the simple operator with the Liouvillean, it becomes more and more size increases. You can think of as, for example, the scrambling time scale. You can think of as many number of n's after which the operator goes to full system size operator. So for this n value, it has scrambled fully, so it will associate with the scrambling time scale. There is no direct relation between n and t that I know of, but this is how you can think of it. That, and these things are, these comments are made more in terms of by looking at different behaviors. But before scrambling, you can directly relate the n and t, because scrambling time is the time known in which the operator is scrambling and reaching the full system size. That is what happening after these many iterations on the operator with the Liouvillean operator as well. Okay, so what happens in open systems? For example, for d equals to or n equals to 6, d was 2 to the power 6. This dimension of the Coulomb space will be basically 2 to the power 6 square minus 2 to the power 6 plus 1. Should be somewhere less than basically something like 4033 or something. And this indeed is the case that we have seen very. Okay, so in case of open systems, we don't know exactly what could be a very good model of how a system is interacting to a bar, but what we want to be is the Hamiltonian that we had. We would consider that Hamiltonian as our system Hamiltonian. So if you remember, my GKC equation was of this kind. So again, this we discussed, this was the unitary part, and this is the not or Hermitian part, and this is the non-Hermitian part. And the corresponding operator evolution also one can write in this way actually. This will change to a Heisenberg picture, this will change, this sign will change, and there will also be some change in the next part, just some L alpha, I think L alpha diagram will come here and so on. But similar expansion, very similar expansion. So what we can do is, again we can write this as some this equation as, or this equation rather, as some ILO acting on operator at OT. This is similar to the Heisenberg equation notion that we had in earlier case. But here this LO, instead of this only this part, will also have some non-Hermitian parts, I multiplied by something. And this Lindblad operators will put in definition from earlier literature as well, that we have to assume some kind of Lindblad operators through which, let's say, my system Hamiltonian is interacting with the environmental Hamiltonian. That we do by choosing this kind of Lindblad operators. Let's say I call L minus 1 with some coupling. We will not consider other couplings like gamma alphas here, but we will already sort of absorb the coupling here. So these kind of couplings will be These are the boundary dephasing operators, known as boundary dephasing operators, that this interaction is happening at the boundary. And we could also have some bulk operators, let's say I, where I goes from 1 to n. It should be this number. So these are my model operators through which I am assuming some kind of interaction with some unknown environment. And this is the equation of motion that it follows. So you know now this full form of LO. Apart from this HS part as well, I will have my this kind of L alpha operators where I could take sum over all of such operators, acting on this kind of things. And then we will have to basically again form a Kilov basis with this definition of LO, which is my Lutvian, more generally known as the Lindbladian for the open system. But here we have seen that the Lanczos algorithm, the tridiagonal way of doing Lanczos algorithm will not work actually. It will not give rise to a fully orthonormal basis because the bras and the gates in a non-Hermitian, because this L0, O, in an open case is a non-Hermitian operator. So it will evolve the bras and gates differently. In situ dagger is, dagger is not equal to L. So basically one has to construct something called a double Kilov basis by acting on the similar Lanczos steps on bras and gates separately and coupling them together so that the basis that you get is consistent. In this way, basically the difference that will happen is B1s, and here also we used to get B1s, we will get something like C1 in the most general case. Although in our case for this model we find that B1s and BNs and CNs are same, but these are not the only difference that you get. You also get, since there is a non-Hermitian contribution over here, it also results in some diagonal components. So previously L acting on OM, we are having something like from Bn to A minus 1 and Bn plus 1 to An plus 1. Now we also have something called like An, and because apart from the commutator I have other terms, and this will give rise to this diagonal terms, which let's say denoted by A, and so we find that in this particular case that we studied, Bn's are equal to Cn. From the algorithm itself, one can guarantee that mod of Bn's should be always equal to mod of Cn. But this is sort of the case we studied that seems to be a special case where the numerical values also match before taking modulus. And this An's will always be some real number multiplied by I. So this will be purely imaginary. So this you can, and Bn's will keep being real like it was before. So Bn's and Cn's are real, but this purely imaginary diagonals sort of give you a notion that your system is non-unitary, it is open system, and so on. And in fact, what happens is if you do this again, write the phi n differential equation. For the most general case, I had this Bn plus 1 terms, but I will also have a minus In phi n. Previously, I had phi n minus 1 and phi n plus 1 terms. And also in the phi n equation of motion, we have a term proportional to Ia. Now, since this An is purely imaginary, I can replace this as in terms of Ia. So there will be plus sign. And then this 2 i's will actually give rise to a minus An kind of term. Okay. So this minus An phi n, and if you forget about these two parts, this phi n dot equals to minus An phi n, this will give you a behavior like e to the power minus An t. So this is your dissipation due to the open system dynamics. That it is from the, this comes from the fact that it is interacting with some environment that we don't know exactly, but the operator is not spreading within only the system part that we are considering. The operator also spreads due to these interactions to some environment part, and the operator spread, that part of the operator spread we cannot take care of. So the probability will also go down. So this becoming 1 will not be 1 anymore because this is non-unitary now, and the probability if plot is basically this I call PT. This PT versus T. First you will see that it starts from 1 at 0 times 0, but it comes down to 0 depending on how large or small this couplings alphas and gammas are. So what happens to the complexity and Bn due to the freedom if you plot the Bn's and Ans? Ans sort of don't distinguish between the, let's say I am plotting the magnitude of A, they don't distinguish between the integrable and chaotic case at all. It goes up and stays saturated. Bns distinguish initially like it used to before scrambling time, but afterwards both Bns show now large fluctuations. Previously, remember that the integrable case showed fluctuations, the chaotic case didn't. So these fluctuations are sort of, you can think of this, we discussed in case of open system parameters, this fluctuation dissipation theory. These fluctuations are a result of that fluctuation that arises in open system dynamics. And this is, you see, the Bn versus in blocks. So from these fluctuations, you sort of cannot distinguish the integrable and chaotic cases after the stamping time. And the corresponding complexity if we plot, this is to be the closed case complexity. You will see that the complexity growth will be still due to this part, the complexity, early time complexity growth before the stamping time will still be more for the chaotic case than the integrable case. But afterward, it doesn't show this linear growth part or this saturation part in this way. What it happens is, primarily also remember that the complexity you have to define a renormalized complexity which is the sum of this time. Only if you plot this thing, this will again go to 0. You have to divide it like we used to do in hormone ensembles. You have to divide it by this probability. And then the behavior complexity of both of them, even after that renormalization, both of them come here and saturate at some constant value very quickly. In fact, here this time scale even before Heisenberg time scale. So there is no Heisenberg time scale if you have open system dynamics. Just after scrambling time, both of them decay. They stop growing, they decay and saturate to some lower saturation value, which is seen for both the integrable and chaotic case. What we get is that understand from this is that after scrambling time, even this part of thing will start becoming less distinguishable if you increase the alphas and gammas through which you control how much it is interacting with the environment, how much coupled it is. So the notion of chaos and integrability sort of becomes unclear after this point of time. If you have small coupling, even if you have small coupling, if you have larger couplings, then even this kind of distinguishability will not hold. But at large times, there is completely no distinguishability between integrable and chaotic cases. So all the information that the system had about whether the system part was integrable or chaotic, it lost that information when it interacted with the environment. Sort of it always saturates to a same value, indicating that both of them have come to, let's say, some kind of thermal equilibrium with the environment or thermal bath that it had started. Yeah. So this is sort of the first problem that I wanted to talk about. Now let's, for last 15 minutes or so, we'll just discuss very briefly something that I said I talk about is what happens if one tries to study a open quantum field theory that we were studying for the last few days, or few lectures, and considers a holographic bath. So by holographic bath I mean that the field theory that it is coupled to is thermal field theory and strongly coupled field theory. So now go to which is open field. So again, yeah. What holography does is plates, strongly coupled QFT in d dimensions, d space-time dimensions, to a weakly coupled gravity theory, quantum gravity theory in d+1 space-time dimensions. And we study the, let's say, the low energy effective field theory version of this QFT. It is in fact related to a classical gravity theory. With some negative curvature also. So when I say open QFT coupled to a homotropy path, I'll basically assume something like this. Let's say I have some degrees of freedom. Let's say my QFT that I am considering as my system is just a QFT with one bosonic degrees of freedom. In 4 dimensions or it could be in general dimensions. And my environment is another field theory, but which is thermal and strongly coupled. For example, we could consider to be some thermal large n equals to 4 super Younglings, or another example that we know of is the large singular charge 2bc. The corresponding bulk duals for this thermal CFT or n equals to 2 super Younglings will be basically a black hole in ADS 5 cross S5, and for this we'll have a black hole in ADS 3, the dual theory. So the idea that this I'm basically talking from this paper that I remember. I will not go into the details at all, I just mention the interesting facts that they explored in this paper. This is a quite detailed paper and you can find more details there, but these are involved as well. So this is by Chandan, Yoga, and Ramadan. So the idea that they go forward with is basically that this will be equal to some black hole in gravity, and let's say if I have the couplings between the system and the environment that I will consider is they consider is basically something of this kind. Where these are basically some gauge invariant single phase operators. Which are the typical operators that one deals with while talking about homotopy. And basically, yeah, you could, in terms of this case, you could think of them as being some low line single phase conformal primary operators. Conformal operators with some primary operators of some dimension delta. And basically the idea that they push is that influence functional. So I will have a total action for Schwinger-Keldy's that will consist of both the system and environment. I will have to integrate out the environment degrees of freedom, and then I will get a influence functional which will give rise to this non-unitarity in my system Schwinger-Keldy's action. For this, let's say psi field will give rise to some S, say psi r, SIL and SIF. Now, what we are doing here, we are in, getting this influence function. We have integrated out this uh, environmental degrees of freedom which correspond to the black holes. So this integrating out means I am taking integrations and so on those variables. So those integrations are the influence functionals. You can actually they motivate that this can be related to certain expectation values of operators, Schwinger-Keldy's kind of expectation values of operators being computed in the black hole. So this influence function or influence phases, remember I write these as IF, these will be encoded in Schwinger-Keldy's correlation functions. Of the environmental operators. They give a description of how to perform Schwinger-Keldy's gravitational setups. So gravitational setups, what we will have to do is basically we have, let's say, I described previously that if I start from a thermal density matrix, so my initial state will be a thermal density matrix of the environment coupled to some initial state of the system. And in that case, the Schwinger-Keldy's contour will be this, that I have to come here, but I also have to come down to make sense of this q bar minus beta h bar. So if I start from 0, here I have some I epsilon, and this total part will be my I beta. So basically this part has to be some minus I beta minus 6. And yeah, so they relate these kind of Schwinger-Keldy's contours to the Euclidean path integrals. If you remember, and they basically deal with planar ADS-Schwarzschild black holes. So for planar ADS-Schwarzschild black holes, the Euclidean path integral is known to have Euclidean cigar kind of construction, where at this point is basically the black hole horizon. This is the radial direction, and the time is compactified. And so, but this is Euclidean. So, how to go from Euclidean to Lorentzian? By Euclidean, I can mean that my time scale, time I have gone to some imaginary time. Then to basically compare to some Lorentzian time, what one does is that it has to cut open this time integration or this time direction at some point near t equals to 0, and basically give rise to some imaginary part in the Euclidean time. Then that will mean again you are again dealing with some real time correlation functions with imaginary part in the real time. So in fact, this sort of makes sense of the Schwinger-Keldy's correlation function in this way, that you take a cut open the slice here, and then you will have to basically this you can think of as the contour in the boundary, but we will have to deal with some gravitational contour. So this gravitational r direction is, for example, in Euclidean path integral of this linearity Schwarzschild black hole was in this direction. So my total contour also has to be of this polarization 1 from this boundary contour that I have. So I have to relate this, identify this part here. In fact, there will be two such sheets, one from this end and one from this end, and then it will have a nice geometric structure which you have to perform. In fact, there are some branch cards here also that they describe. So, say your RH is of this kind. I should mention a couple of other things, that in a, let's say, internal black hole Penrose diagram, what this means is something like this. This is my horizon. I'll only deal with T going up in this case. let's say this is my right operators. This is for my right operators where time is going up, and this is for the backward time evolution part, this branch where basically we lift operators again. And so the way to understand this is basically we are considering this part. Remember that we are not dealing with homofield doubles, so we will not be bothered about this left half of the Penrose diagram. We'll just be bothered about some t going to after 0 and take this part. Here, let's say my Hawking quantas will be ingoing towards the horizon, and in similar setup, in this part we'll have to consider time coming backwards. Hawking quantas have opposite direction, and basically what we have done is associated, identified this horizon with this horizon and made a time shift of this kind. This part is this horizon can be treated as this part of the figure, which is also local dimension one surface is connected to the horizon. So all of these kind of detailed mechanisms they describe in the paper, and in fact this is needed basically. Otherwise, if we are in some equilibrium situation where my density matrix was not going out of equilibrium, it stayed in some equilibrium, then there is a similar construction but not exactly similar. There one does start from 0, but this is like minus, instead of I epsilon, here one takes minus I beta over 2, and there another minus I beta over 2. This kind of fingerprint contour is known to give a thermal state preparation or a thermofield double state preparation. But since we are talking about non-equilibrium procedures, such contour will not work, and one has to always end up doing this kind of dealing with this kind of contour, which is the fingerprint contour. And in fact, let me now just see the final results, and over that. When I say planar Eddington metric, they built the metric in a Eddington-Finkelstein coordinate. Square V square with the ingoing Eddington-Finkelstein coordinate V. So again, this ingoing, only the ingoing coordinate ensure that you have explicitly broken the time inversion symmetry, which is also broken in any fingerprint procedure, because you are not actually going to t minus infinity. You are just taking the t plus part and taking the backward evolution of that. And the final result that they talk about is basically, if you remember while talking about the influence functional, which was a mixed part of a mixed kind of thing, then I wrote in case of phi r, phi n in the last day as well when discussing this phi cube thing, I said that I considered that to be local because there was no clear notion of why it should be local. But if it is local, what happens is the effective field theory in the system part that you get is a local open effective field theory. But it is not, in general, one would expect it not to be local. There is no reason to expect that it to be local. But they find that in such case, if you take a holographic bath and you compute everything, you compute influence functionals by considering such gravitational fingerprint contour. Basically, what we have to do is for computing correlation functions, we have to introduce operators here and here for two-point correlation functions. We have to compute some bulk to boundary propagators through these computations are done using the Witten diagrams. They did using Witten diagrams, and you can compute these things, and you can talk about all kinds of influence functions where phi r and phi l's are mixing kind of fields. Then what they get is that this influence functional for a holographic bar is in fact a local influence functional, so it doesn't have any non-local terms, and then it helps in describing this open quantum field theory, or rather open effective field theory, low energies, because that's where you can deal with the bulk dual as being the classical gravity theory as a local opaque because whatever we learn in quantum field theory, in most cases we are mostly equipped with dealing with local theories. So it is in general hard to deal with non-local theories. So in fact, in this case, these holographic thermal baths are good in that sense that you can uh, describe these systems that it is attached to a local effect, open effective field theory, and these behaviors are also described. Yeah. So this is what I had in mind for today. And to summarize, we basically started by describing quantum mechanical systems, where I integrated out a part to deal about some system part only, and described that non-unitary evolution through this GKSL equations or Lindbergh equations. We also saw this Langevin dynamics. So I should also say that from this holography bath study, we also they had a nice description, stochastic description, where they could talk about the fluctuations and dissipations coming in the theory, how they come into the theory and so on. So we will not go into there, but that relates to what we discussed, for example, in this Langevin dynamics part. That was a non-quadratic study where we came across this fluctuation and dissipation terms. And so the GPS equation was for Markovian case, the Markovian assumption, where the system dynamics shortly because it dissipates very quickly, which we saw, for example, from our field of complexity studies that I described today as well. That it goes up but comes down very quickly and remains saturated or equilibrated with the environment. But there could be non-Markovian cases also, which we sort of discussed, where we long live. And in this holographic paper, they in fact talked about this non-linear and non-Markovian cases as well. And for QFT, then coming to QFT, this was also a nice example of how to deal with this GKS equation and how you can in fact apply such equations in studying certain quantities. In QFT, we learned about the Schwinger-Keldysh contour, why it is needed, because in vacuum is not equals to out vacuum, and for a system part we saw that the Schwinger-Keldysh action, apart from this phi L, phi r and phi L, will have an influence function part which is a mixed term, this phi r and phi A, and this term gives rise to the non-unitarity in quantum field theory studies. We discussed then some Feynman diagrammatics, cutting rules and so on, which came to rescue when we were using the out of time ordered coordinators in open quantum field theory using the Schwinger-Keldysh contour. So Feynman diagrams, it's complementarity, and Feynman rules. Mainly we studied two such examples. One was open light cube theory. We saw that the result of it being open was actually we came across the openness through the non-local divergences that were not present in a unitary phi cube theory. And finally, we, from our example that we briefly talked about today, we have a holographic part. One can know systematically about gravitational fingerprint disruptor, which probably I didn't talk about in enough details, but you can look at this paper that I wrote down earlier. And with blackboard metric in link and sign coordinates. And this actually came out as good thermal baths, in the sense that the open effective field theory for the system, that after integrating out this part that we get is actually a local field. So is the influence functional is also local. This would be the overall summary of what we discussed. In between, we also discussed what is the general definition of quantum channel, which might be useful in talking about quantum information theory, quantities, and so on. Yeah. There are